What'd you say? Okay, a magnetic force. Okay. What makes things fall? Gravity, right? There is a gravitational force. Thank you. Anytime that I push or pull on something, right? Am I applying a force? Is there a specific name for that type of force? Not magnetic. A contact force. Or really, we'll just start calling these applied forces, right? I'm applying a force. So those are kind of basic pushes or pulls. Something where you make contact can be just called an applied force. Okay, how does forces affect an object's motion, right? It can change a lot of things about an object, right? Frictional forces cause objects to do what? Speed up or slow down? Frictional forces cause an object to speed up or slow down. Slow down, right? Applying an accelerator type of a force, right, would cause an object to speed up, right? What would cause the direction of an object? What would change the direction? We're not going to deal with magnets. What would change the direction?
Like the ones that we...
A steering wheel?
Like the water. The ones that we were doing.
Like a projectile?
Yeah, no. The one where we like...
The current?
Oh, okay. Okay, relative velocity.
Yeah.
Okay.
That was hard.
What I'm thinking of is if something is moving and I push it, it will change direction, right? Applied forces cause a change in direction too. Okay? So, lots of different things can change the motion of our objects. A couple vocab words that I didn't have you do that I want you to just be a little bit aware of is the system is anything that's being manipulated. The object that is being manipulated is called the system. All right? And then the thing that's doing the force, thing that's causing the force is called the agent. The thing that's having the force applied, the agent is the thing that applied the force. Okay, so I push this book. What's the system?
The book.
The book. What's the agent?
You.
Me, right? Or my hand, right? Whatever. Okay? All right, we're going to talk about Newton's first law. Can anybody tell me what Newton's first law is?
Everybody's...
The law of...
Motion.
No, not just motion. It's like very common.
An object in motion stays.
Okay, yes. Do we know what that's called?
Relative.
No. Inertia. Good. The law of inertia. Newton's first law is also called the law of inertia, which means everything stays in motion that's already in motion. Everything that stays in rest is already in rest. So here's the long version of it. There's the short version of it. Right? You need to know that Newton's first law is the law of inertia, and that it has kind of that short. You can even just remember that short definition. That's fine. Inertia, I believe, was a vocabulary term that we took notes over, or that we did with our partner. So Newton's law of inertia applies for a perfect physics world. Right? What would be realistic things that change this or that are contrary to this? What would be real life things that might cause this not to be true? When you roll a ball, will it go forever and ever and ever? Well, what would it stop because of? Friction. Right? So this is perfect physics world. It says, unless acted on by a non-zero force. So the frictional force would stop that, right? Would slow down that ball. And so when we say objects at rest tend to stay at rest, objects in motion tend to stay in motion, that is true. And it's true when there's nothing else happening to them. right? No friction, no air resistance, no nothing like that. Okay? Inertia was a vocabulary word that I had you look at, I think with your partner. What does inertia mean? No. There's a definition of inertia itself.
The tendency of an object to resist moving, or if the object is moving, to resist the change in speed.
Good. Inertia means the tendency of an object to resist change. Okay, it also describes high schoolers, right? The tendency of an object to resist change. Right? Okay? When you're in bed, you want to stay in bed. When you're in motion, you want to go back to bed. Okay, so I guess that doesn't really count. Okay? Tendency of an object to resist change. So all that means is once an object's in its path or in its motion, it doesn't want to stop. And once an object is at rest, it doesn't want to get started. All right, this next slide I want to just go kind of quickly over so you don't have to take notes over the next slide. But I wanted to remind you about a couple things, okay? Forces are vector quantities, which means they need to have magnitude and direction, just like acceleration, just like displacement, velocity, all that kind of stuff. Okay, they are vector quantities. They're represented by an arrow, just like usual with vectors. The direction of the arrow is in the direction of the force. So if I say I apply a force to the north, you draw your arrow to the north, just like we've done in previous chapters. It's going to be our goal to draw to scale again, right? We talked about a proportionate scale, so we don't have to get out a ruler and measure it. But if one force is 5 and one is 10, we need to make sure we draw that to scale. Okay. The last one, you need to probably write that down, is the units for force is newtons. Newtons. Okay, and I'll show you where we get that Newton here, but it's a capital N that we abbreviate it with. Okay. So you need to make sure that you're not mistaking that for north, right? That's going to be the unit that's attached to that. Okay. All right, you already have this, I think, a little bit. What's a contact force? Yeah, it's anything that is applying a push or pull that comes in contact with our object. So you don't have to write this down, but anytime we push, hold, pull, or do anything in contact with our object, that's considered a contact force. A field force is the opposite of that, so things that are not coming in contact with our object. Can you give me an example of that? Okay, air resistance, good. Gravity, good. Magnets, yep. Okay, yep, all of those things. Yeah.
So is action and resisting force?
Yes. Sure. Okay, when we drop something on the floor, it doesn't just float in the air, right? Gravitational force pulls it down. Yet the floor is not jumping up and grabbing that book to pull it down, right? It just falls. So it's a non-contact force. Okay, here's where we kind of get into our new stuff. And so we're going to talk about something called net force. What does it mean to have the net of anything?
Combined.
Okay, kind of combined. Any other terms, or what other things do we see net associated with? Net worth. Net, what did you say? Net growth, net profits, net income. All that means is after everything else has been taken out. Right? Net means the total or the sum of. So we're going to start talking about a net force. Okay, it is the sum of all forces acting on an object. It's the final result. If we think about net force as like a tug of war scenario, right? The net force is where is it going to end up? If our net force on our object is 0, what does that mean is probably happening? Okay, one scenario is that it's not moving. The second scenario is that when it is at constant velocity. If we have an object moving at constant velocity or at rest, we see a net force equal to 0. Okay, so I would write that part down. That if we're at constant velocity, our net force is 0. And that's what equilibrium means, is when our net force is 0. So we're going to look at how we draw, how we look at force diagrams, and then we'll kind of get it back into the math. But sorry, I still see some people writing. I don't want to go too. Okay, we're going to look at how we draw force diagrams, and force diagrams are called free body diagrams. Okay, free body diagrams. We're going to look at how we draw all of our forces. Okay. So, for all of our force problems, we're going to have to draw a free body diagram. It's going to be super, super important. But we need to know every place that our object has a force exerted on it. Okay? So, we're going to make a model. We're going to identify every place the system touches the external world. So, whatever forces are acting on our object, we have to show in our free body diagram. Okay? We have to show. We're going to draw our forces as vectors in the direction of the force applied. Oops. So I want you to look at what's happening here. Okay? It's the same object. We're going to label each force. We're going to remember our forces are drawn to scale, and they should be pointing away from the object. So in this picture, in this model, we've got this book. Okay? And we represent our object by a dot. You don't have to draw out the book every single time. What's happening to the book? Is it being pushed, pulled, lifted? What's it doing? It's being pushed, right? And it's being pushed to the right. Okay, you see this hand pushing the book, being pushed to the right. Okay, so what I would call this, instead of force of hand on book, which seems a little bit, unnecessary, I would just call this force applied, right? Because it's some applied force, APP. Okay, that's what I will label that almost all the time. It's any sort of force that's push or pulling, force applied. Okay? What do you think another name for this force might be? The force of the Earth's mass on the book. Gravitational force. So we don't write it like that. We're going to write it like this. Force due to gravity. Okay, does that make sense? Force due to gravity. And then our last one up here tells us that if gravity is pulling downward on my book, yet it's not falling, right? It's still sitting on the table, which means the table has to be applying a force upward on the book to hold it in place. Okay? We're going to talk about that in a little bit, but really this is going to be called what we call the normal force, F sub n. Okay? We'll reassign these names here in just a second. But what do you think our net force would be on this object? Is it going to move up, down, left, or right? Right. To the right. Why would it not move up or down?
Because there's a force being applied both ways.
Right. Are these vertical forces congruent? Right. Our book is not moving up and down. It's resting on the table, which means the table is applying just as much force upward as gravity is applying downward. So vertically, it's in equilibrium. Horizontally, it is not. Horizontally, it would be accelerating to the right. Okay. Does this diagram show that we're counting for any friction? No. If I had friction here, where would it be applied to? Where do you think the friction, what direction would my frictional force go to? This way. Right? Friction would counteract or would oppose my motion. If we had friction, it would be opposing my motion. So we would draw it in there. But this diagram doesn't show any friction. Okay, does that kind of make sense how we're going to draw these? Did you see that our diagram was not drawn this way? We didn't say, here's our object, gravity's pushing it down, normal force is pushing it up, the hand is pushing it to the right. Right? Do you see the difference there? Yeah. All of our forces should be drawn stemming from the object and outward. Okay? All right. Let's try a couple. Draw the free body diagram of a box accelerating in the rightward direction. Include frictional forces. Okay? So let's just start looking at how we draw this. We don't have to draw the box. Okay, I draw my object with a dot. You can draw the box. Okay, what do we know has to be acting no matter what all the time?
Gravity.
Always have to be having gravity. And we label that how? F, G. Okay, it is probably sitting on a surface of some kind. Do we agree? The box is probably sitting on a surface. It doesn't explicitly say that, but we're going to assume it's sitting on a surface of some kind, which means that surface has to be exerting a force upward. And we call that the normal force, right? The normal force. We're going to talk about the normal force later a little bit, but we're going to assume that it's sitting on a surface and that surface is exerting a force. Are these two forces, do you think, equal to each other?
Yes.
Yes. We're going to just assume the box is not going to go flying through the air vertically. Okay? So remember these lines, you remember what these lines mean from geometry? Those are congruency lines. So they're going to say, you don't have to put those in there. It just gives me a good idea that you understand those two forces are equal. Okay? Now it says we are accelerating to the right. So what do we know about our rightward force? It says it's accelerating to the right. We have some applied force then. F applied. And then what do we know about friction? Do we include friction? Yes. And so it needs to be going to the left. Should our frictional force be greater than our applied force or less than our applied force? Less than. How do we know that?
Because it wouldn't be moving if
Good. If these two forces were congruent, it would be moving at constant velocity. Which means when I move at constant velocity, okay, if I move at constant velocity, that means with every push, I'm doing just enough to overcome friction. And I'm putting it in motion that way. When my book accelerates, right, I'm doing more than friction. Does that kind of make sense? When I move at constant velocity, those two forces would be equal to each other. Okay? But since I'm not moving at constant velocity, it says I'm accelerating in the rightward direction. That means my applied force has to be greater than my frictional force. Okay, are we good with that? Yeah, go ahead. Okay. All right, a car coasting in the leftward direction and slowing down. A car coasting in the leftward direction and slowing down. Okay, what does it mean to be coasting? What do you have? Do you have your foot on the gas or the brake? Neither. Neither. So let's think about what's happening to my car vertically, because we always need to be considering vertical forces. What's happening vertically to my car? Anything?
Gravity and...
Right, I always have gravity, and my car, I hope, is on a surface. And so that means my normal force and my gravitational force should be equal to each other. Do we agree with that?
Yes.
We will have situations in which they're not equal. Yeah, we're going to look at that a little bit later. Brody, what was your question? I'm sorry. I thought you asked a question. Oh, I don't know the answer to that. All right, so if we're coasting, we're not applying the gas or the brake, so what's slowing my car down? Friction, right? And so we assume that this is we're coasting in the leftward direction. We're slowing down. So what direction should my friction go? To the right. Does it really matter how large we draw that frictional force? No, it just needs to be longer than the one over here, and there's nothing over here, so it can be as long as you want. Okay? Well, when we say coasting, that means we're not applying the gas or the brake. So we're not applying any sort of forward force, because it says we're going to the left. We're not applying any sort of leftward force. We're letting friction just slow us down. Okay? Yeah.
Is there friction on ice?
Friction is reduced to a smaller amount on ice, but yes, technically there is some.
Is there any object that doesn't have any friction?
Joints in your body have like one of the lowest coefficients of friction that we know, right? You wouldn't want friction in your shoulder joint. Agreed? Okay, so there is something called a coefficient of friction, and coefficient of frictions give us the kind of value of two what am I thinking? Two surfaces on each other, and so I have a chart that we'll look at reduced coefficients of friction. Ice is low, but like bodily joints are really low. Like lubricated steel is really low. But yeah, ice does have some, just not a lot. Okay. All right, now we're going to find out, how do we calculate net force? How do we calculate the net force? What does the net mean? What did we say net means? The overall, the sum of. Okay, so you can just kind of look at this. You can jot it down if you want. But net force is, believe it or not, like pretty easy to calculate. Okay, if I take the net force on this first object, I'll show you kind of how we write it out. We always say F net is equal to the positive forces minus the negative forces. Right? That's it. That's what net means, is the before minus the things that get taken out. I don't know how you say that, but yeah.
So it's like resultant vector.
It's very similar to a resultant vector, except here we're really going to have things very clearly in horizontal and in vertical form. So yeah, good question. Okay, in our net equation, we're always going to take the positive forces minus the negative forces. Okay, positive forces minus negative. So does it make sense here that our net force is 0? Okay. The second one here, the way they drew this is kind of silly. I mean, that's whatever. But what it would really look like in this instance, I'm going to draw number 2 over here. Okay, it would look like this. Here's my object. Here's force 1. Here's force 2. Right? So it should make sense to us that our net force is 200 newtons in the positive direction. Right? Here, we're not accounting for vertical forces, but when we do that, we'll have a net vertical force and a net horizontal force. Just like in projectiles, we have to analyze them totally separately. Yes. Right. For our initial problems, yes, but we're going to eventually have problems where things get lifted, and so then there's not a vertical net force of 0, right? You'll have a net force. So, okay, and this one, does it make sense? We take positive forces minus negative forces. Right. So you could say it's negative 100 newtons, or you could say it's 100 newtons to the west, or whatever you want to say. Okay? Does that make sense? That's a really, really important concept for you. Write it down if you need to, but net forces is positive forces minus negative forces. I'll say it over and over and over again. Okay? Net force is very similar, yes, to our resultant vector. All right. So you don't have to write down this whole definition, but you do need the equation that goes with it. Okay? This is Newton's second law, which says the acceleration of an object is directly proportional to the net force acting and inversely proportional to its mass. Okay, and so all it's saying is that F net equals m times a. Okay, I want you to put in that F net right here. Net force is equal to mass times acceleration. If you would like a new equation sheet for this chapter, I have just a few up here, or just add that to your old equation sheet, but you will need to put that on there. There's just a couple equations for forces. Not a lot, but a couple. That's one that you should maybe put on there. If you want a new one, come up and grab one. Right? Net is the sum of the forces, and it's also mass times acceleration. So what will really end up happening is we'll do a substitution in our problem. So if we say F net equals 100 minus 200, like in our last problem, we would go ahead and substitute right here to say MA equals 100 minus 200. Does that make sense what happened there? Both of these things are equal to F net, positive forces minus negative forces. F net is also equal to mass times acceleration. So we just do a little substitution there. Okay, this would be like if we wanted to solve for the acceleration of our object, or if we needed to find the mass of our object, or whatever. Does that kind of make sense how that works? Okay.
F net is equal to MA.
F net is equal to MA.
So whatever F net is, MA is that.
Right. Right. So you could find the number here first, negative 100, and then you could go set MA equal to negative 100, but it just saves some time to just do it in one equation. Mass times acceleration. F net is equal to MA. We're going to do this over and over and over again, but I want you to see where that substitution takes place because it's super important. All right, the units we said are newtons. Newtons come from the fact that we take kilograms times meters per second squared. Okay, so That's what a Newton is. 1 kilogram times meters per second squared, and they just abbreviated it rather than having to write that guy out the whole time. Okay, not a huge deal, but that's where it comes from. Okay, let's do some practice. Find the net force. Find the net force needed to accelerate a 1,000 kilogram car at 4.9 meters per second squared. So, yeah, that's it. Okay, I don't need to draw my diagram here necessarily. I can, but I don't need to. I don't know if there's friction or not. All I know is that the result acceleration is 4.9. So A is 4.9, M is 1,000. So my F net is, right? We said newtons is kilograms times meters per second squared. So my result will be in newtons. So all of that's saying is that this is taking into account if we had friction, if we had a brake, if we had a gas pedal, whatever. Right? All it's saying is that the result net force of that would have to be equal to 4,900 newtons in order for my car to accelerate at that rate. What'd you say?
This may be a dumb question.
To rest from a speed of 100 kilometers per hour within a distance of 55 meters. Right, this has a lot of things. Yeah, we've got a couple different things that are going to affect our problem here. First of which is we don't know our acceleration. How can we find our acceleration?
Oh,
I have a velocity. I have a distance.
yeah, but we could also we know what F of net is, right?
Do we?
Yeah. 1,500 times 100.
Nope, that's kilometers an hour.
That's
Not squared.
that's a velocity, not an acceleration.
Never mind.
Good try. That's okay. Okay, so let's start writing down what we do have. We have mass. We have our initial velocity, 100 kilometers per hour. How do we go from kilometers per hour to meters per second?
Divide by 100.
It's like 3.6.
Divide by 3.6. 277.8. And what's our final velocity? What's our final velocity? 0. It comes to rest. So it's 0. What does that 55 tell us? X final. So can't I use a kinematics equation to solve for A?
Technically, yeah.
Technically. That's right. I told you it's never ending. Kinematics we'll use like almost every chapter. Okay? So go ahead and solve for A for me. It's not a projectile one. You just use your regular equations, regular kinematics equations. Go ahead and solve for which? Go ahead and solve for A. You're all going to have to do this, so you might as well just do it now. Okay, so our velocity should have been 27.8, not 277, which means our acceleration is -7. Okay, so now if I'm going to solve for my net force, I'm going to say F net equals M times A. Why does my net force come out to be negative, or what does it tell me? What does my negative net force tell me?
It's slowing down.
It tells me it's the biggest force acting is either my frictional force or my braking force, right? Or a combination of those two things. Okay? It's telling me that the force that is overriding or whatever, the net force is in the negative direction. It is opposing my forward motion. Is that rational? Does that make sense? Okay. All right, now we're going to look a little bit at the difference between mass and weight. We're going to switch to vertical a little bit. Mass is a quantity of matter. Mass is measured in what?
Grams.
Okay, but for us, it always needs to be in kilograms. Kilograms. Always needs to be in kilograms. Okay, sometimes mass is described as the measure of inertia of a body. So the more the mass, the more resistant to change. Right? The bigger an object is, the harder it is to slow it down, or the harder it is to get it started. Okay? Those are some things we need to know about mass. Measured in kilograms, it's kind of a measure of inertia.
So is that what, like, foreign countries?
They measure in kilograms. But, okay, everybody on the scale, okay, the scale is a little bit different thing for us, but everybody measures technically mass, right? But our weight is really measured in newtons. We just use the word weight incorrectly, like all the time. Weight is how gravity affects our mass. And so we use the word weight universally wrong. Okay, weight is a force. It's how gravity affects our body, or how gravity affects the mass. So you don't want to hear your real weight, because it's about 10 times heavier than your actual mass, right? You should not describe yourself in your real weight. Okay? Things weigh less on the moon because gravity is significantly smaller on the moon. Agreed? When you go to the moon and you're like floating, did you lose kilograms? Right? Part of your body didn't just go away. You just have less of an effect of gravity, so you would weigh less, right? If you stood on a scale on the moon, your weight would be significantly less because you're not having this pull of gravity that's pulling you down. Okay, but you're not losing pounds when you go to the moon. Mm-hmm.
How high was your
Something's weight, we take mass times little g, which is the acceleration due to gravity. So you need to write this down. Write it on your equation sheet or whatever. But Fg on Earth would be mass times 9.8. Right? On Earth, g equals 9.8. Whereas on the moon, g would equal 1.7. Right? In between the Earth and the moon, it might equal 3.5 or whatever.
But it's not negative.
The negative does not need to be included here because we're always going to draw it in the downward direction, right? Negative tells us downward, so we're going to draw it downward on our diagram so we'll know. Okay, does that kind of make sense? So weight is, if you weigh 100 kilograms, your weight is 980 newtons, right? Not something you really want to talk about, okay? But your mass itself doesn't change when you go farther away from the center of the earth. Okay, so when I solve for weight, it's given to me in newtons. So if I say something weighs 400 newtons, its mass would be found by going mass times 9.8. Does that make sense? If I say something's weight is 400 newtons, that's equal to Fg. So if I want to find out what's the kilograms between that, I would divide that by 9.8. Okay, do we understand that part? Yes, Jackson. Weight is at Fg, so I would take mass times 9.8. Right? We're always going to assume things are on the Earth unless otherwise stated. Okay? And so the weight of that crate would be 588, thank you. And what would my units be for weight? Newtons. Good. Newtons. Okay? That's something that you're really going to have to pay attention to. All right, we're close, I promise. I know this was a long day. Okay? Newton's third law is equal and opposite reactions. Newton's third law is equal and opposite. So if I exert a force on something, it's going to exert the same force back on me. Equal and opposite reactions. Okay, have you heard that term before? For every action, there is an equal and opposite reaction. Right? That's Newton's third law. So today you've done all three of Newton's laws.
You only had 3?
He had 3. Jackson's.
4th law.
Okay, this is just the way this is written out. Not a huge deal. This does not need to go on your equation sheet. All it says that if object A exerts a force on object B, then object B exerts an equal and opposite force back on A.
So like a push-up.
The force that you're exerting on the ground is exerting the force back up on you.
Yeah.
Right. All right, so I'm going to run you through a math example here kind of quickly. So, do we have what we need on this one? All right, so I want you to look at this diagram. Can you see it okay or not? No, I don't need to turn all the lights on. All right, here we go. I'm going to go through it kind of quickly. So, we're going to assume that the box itself weighs, let's call it 10 kilograms. Let's say the box weighs 10 kilograms. So in this first example, what would be, if I set up my net force equation, F net equals positive forces minus negative forces. Do we see how that works? Fn, they don't have their free body diagram drawn correctly, but that's okay. Fn is pushing upward, Fg is pushing downward. See how I did positives minus negatives? Do you see with that? Okay, would my normal force and my gravitational force be equal in that example? Yeah, my net force is 0 because my object is not in motion, it's not accelerating. So Fn minus Fg, really Fg would be equal to Fn. Do you see how mathematically that works? If my net force is 0, my normal force and my gravitational force are equal. So to find my normal force there, I would just need to find Fg. Fg is equal to 10 times 9.8. Okay, so my normal force would be 98 newtons there. Does that make sense how they're equal to each other? So, well, my whole goal in all of these is to find Fn. Sorry, I should have stated that a little more clearly. My whole goal is going to be to find Fn. In the second example, I have now a pulling force. I'm pulling upward on it with 40 newtons of force. So if I set up my net force equation, it would be F net equals Fn plus F pull minus Fg. Does that make sense how I added those two positive forces together? Normal is going upward, pull is going upward. So now my normal force is not going to be 98 because as I lift upward, I'm taking pressure off the normal force. Does that make sense? So let's look at what this is. My net force is still 0 because my object has not been removed from the table. So my normal force is what I'm solving for. My pulling force I know is 40 newtons. Fg I know is 98. My box was 10 kilograms. So 10 kilograms, right, it's the same object. Okay? So what would my normal force be equal to? 40 minus 98. Move it to the other side. I would get positive 58 newtons for my normal force. Right? Should my normal force ever come out negative? No. Last example. Fn equal F net equals normal force minus my pushing force minus Fg. See how it's pushing downward this time? Okay, so I'd say 0 equals normal force minus 40 minus 98. So I add those together, and now my Fn equals positive 138 newtons. See, because as we push on that object, the table's having to work harder to counteract that force.
What are the technical rates?
Well, then we'd see a bigger problem.